Hello everyone, welcome to this episode How to Select Remotely Sensed Data in the series of GIS and Remote Sensing. This series is brought to you by the Faculty of Forestry, the University of British Columbia. I'm Haitali, I will be your guide. Remotely sensed data is an essential element of forestry research. It provides synoptic, spatially, and spectrally consistent, frequently updated measurement of land surface character. Most remotely sensed data is collected by satellite, aircraft, drone, or UAV. For forestry, the main data format are optical, microwave, and LiDAR. Optical sensor collect solar radiation reflect from Earth's surface, include land, plants in building. The wavelength usually is between violet to infrared. Optical data is most used data for forestry. The most common microwave instrument is synthetic aperture radar or SAR. So SAR, radar, and microwave image under some conditions are exchangeable terms. The sensor collects the reflected signal emitted by themselves. Comparing to the optical signal, microwave has more power to penetrate through cloud, haze, dust, rain, and canopy. 5 commonly used bands were given name as X, C, S, L, and P during the World War II, and remained to this day. One special character of microwave is polarization. It is a way to transmit and receive signal. Microwave data is sensitive to soil moisture, biomass, forest structure, and surface roughness. LiDAR is getting more popular in this year's research. It provides high accuracy 3D measurement of the distance between sensors and objects. LiDAR is active remote sensing. The sensors are predominantly on airplane. The spatial resolution is about 1 meter or smaller. LiDAR data can be used to calculate individual trees characters such as height, canopy size, timber value, foliage distributions. It is a very powerful data source for precision forestry. Doesn't matter what type of data it is. When we think about remote sensing data, these 4 resolutions have to be considered: spatial resolution, spectral resolution, temporal resolution, and radiometric resolution. Spatial resolution is a measure of smallest object that can be resolved by a sensor, and it represents pixels on image. Usually, coarse resolution is above 1000 meter, a medium resolution is 100 to 1000 meter, a fine resolution is 5 meter to 100 meter, and a high resolution is below 5 meter, but this definition is not strict. Spectral information is the soul of remote sensing data, which make it different to photo. The spectral resolution includes the width of each spectral band and number of spectral bands. For example, the first band of Landsat 8 is 433 to 453 nanometer. The bandwidth is 20 nanometer. And the band 8 is 500 to 680 nanometer. The width is 168 nanometer. The narrow band can catch up with more details of spectral feature. The wider band has a weaker ability to do it. However, it can provide higher spatial resolution image because it collects more energy at the same time. And we call the band panchromatic band if it covers most or all visible light. For multispectral data, the bandwidth usually is about 20 nanometer or wider, and the number of band is less than 100. And the hyperspectral band is 10 nanometer or narrow, and the band number is more than 100. Here is an example. Landsat is a typical multispectral data. MODIST is in between of multispectral and hyperspectral. AVIRS is a hyperspectral data. In addition to the band's width and number, polarizations must be considered when talking about microwave spectral resolution. Also, the recently research developed multispectral LiDAR device. In most cases, LiDAR still only use the band is 1064 nanometer. Radiometric is a number of intensity levels to discriminate the radiance of each wavelength. The intensity level present as a grayscale image. This equation shows the relationship between bit number and level. Here is an example showing what difference the scale images looks like. Of course, no remote sensed data use 1 bit or 4 bits. Almost all satellite images are 8 bits. We cannot choose the radiometric resolution, so we don't need to worry about it. Intensity of laser beam return is affected by angle of arrival range, surface composition, roughness, and moisture content. Researchers use it in feature detections, extractions such as land cover classifications, vegetation classifications. Temporal resolution is a frequency for a sensor to visit the same site, also referred to as a revisit interval. It could be daily, semi-monthly, or anytime. Higher frequency or shorter interval provides more data and has more chance to have clear sky imagery. Temporal extent is the time length of a sensor's work history. For example, the earliest Landsat instrument, Landsat 1, started to work in 1972 and served for 5 years. Landsat 7 was launched in 1999 and still working in space. We already talked about the full resolution. How do we use these characters to select data? Let's start with the spatial resolution. First is the research area. Lower resolution data for large scale area. High resolutions for small area. If the research area covers most part of the Earth, a continent, or Canada, we can choose MODIST, AVHRR, or other data with 500 or 1 kilometer or even larger resolution. If it is regional, such as a city, a national park, forest management area, Landsat, Aster Spot, or Sentinel are the good data for this research. If the area is even smaller, such as a PSP, a card block, or campus, or even a single tree, so we can use high-resolution data such as EGNOS, world view, drone collected images, or LiDAR. However, hyperspatial does not improve the result of classification because the same object falling in multiple pixels, and each pixel may be in different classes. It will confuse the result. To study canopy's spectral character, it's better to use 5 to 30 meter resolution data because in most cases the canopy size is falling in this range. This plot combines both information of spatial and temporal resolutions. We have access to all the data on this plot. However, you have to contact me if you are looking for high-resolution data. Location store absorption features on wavelength axis is unchangeable. This is the reason we can use spectral reflectance to study things we are interested in. Green planes share a number of common features. Low reflectance in the blue and red wavelengths. High reflectance in infrared. This feature was used to develop several vegetation indexes such as NDVI, EVI. Photochemical reflectance index uses chlorophyll absorption in blue and red. Shortwave infrared is good for the studying of leaf biochemistry, protein, and others. However, some parts of the reflectance are blocked by atmosphere moisture. Hyperspectral can provide more details of spectral features. It has advantages in monitoring plants' nutrition, health, disease, stress. It is also sensitive to BRDF, so we can use it to classify tree species based on the different view angle. This plot shows several satellite band distributions on wavelengths. This is a good start point to search your data. Besides the general information, let's talk about the two satellites. First is Landsat and the second is Modest. Landsat 8 started to collect the data since 2013 and still working. It contained 11 bands with spatial resolution from 15 to 100 meter and wavelengths from 433 nanometer to 12.5 mil. Technically, it revisits the same place every day. 3 levels of data are available to download. They are based on data quality and the level of processing. Level 1 data have geometric and radiometric correction. Level 2 is scientifically viable products generated from level 1 data, include surface reflectance and temperature. Analysis ready data, or ARD, are processed to the highest scientific standards and are required for direct use in monitoring and assessing landscape change. For most cases, ARD is the data we want. Besides Landsat 8, 6 different Landsat data are also available. Landsat 9 is coming this year. They are all from the Landsat family, but the data quality and the resolution are different. The earlier Landsat data have less bands, lower resolution. Landsat 7 data may have strippings on imagery. Check the data quality before using it, especially using them for the same project. The first Modest instrument was sent to space in 1999 and continues working on its orbit. The data is low spatial resolution and high spectral resolution, include 36 bands. They are good for land cover and change, surface temperature, wildfire, and other. The temporal resolutions is 8 or 6 day or monthly. Modest data also have ready-to-use products such as snow cover, land surface reflectance, or temperature vegetation index such as NDVI, EVI, and others. You may find most of the data on the website of the Earth Explorer. Please watch the videos how to download the data from Earth Explorer if you never use it. UBCGS provide good resources to find the data. If you are interested in LiDAR data, Government of British Columbia is the best place to look for. And our faculty's shared drive have the lots of data available to download and use. Think about this before deciding. The research object. What questions and problems do you want to solve? Research area. Where is the location, how large it is? Time. When do you want the data be collected? Summer or winter, one-time collections, or 10 years record? Availability. Does data open to download or have limited access or even not exist? Is a computer powerful enough to handle it and have enough space to store it? Last but not least, cost and budget, both time and money. There is no clear boundaries or guidelines to use data. For example, we can use LiDAR, microwave, or optical data to create DSM. We can use any of them to monitor biomass or canopy structure. Instead of a single source of data, data fusions may provide more options. For example, we can use higher spatial resolution spot data with high spectral resolution Landsat data to generate better imagery. Beyond data itself, the ways to ask questions and to solve the problem could bring more power than data. It is very difficult to detect a gene direct from remotely sensed data. However, we can find a clue from phenology or plants' response to environment. Using this information, we can identify the plant's phenotype and then genotype and gene. Think more and keep trying. It is not easy to get perfect answer, but always have solutions to match our goal. Thanks for watching and feel free to ask questions.